Greetings, and welcome to the primer on systems thinking. Whether we realize it or not, and whether we consciously integrate it into our discipline or not, what is known as systems thinking is fundamental to our understandings and practices in any field. In that same vein, it is also fundamental to our approaches to integrate ideas of how our actions impact the world around us at multiple scales, from the very small to the enormous, as well as how we choose to communicate that information to others who may or may not share our common core belief system. In order to consider what systems thinking is, we need to first understand what systems are. A system consists of multiple elements that are interconnected in some fashion and whose interconnections create functions or structures that do not exist otherwise. As an example, consider a government. In the United States, for instance, the government consists of three branches that are interconnected in a system of checks and balances, at least supposedly, and these checks and balances enact and enforce policies and laws. The resulting structure is something that none of the branches alone could create. On a different note, consider your own body. Your organs are interconnected by neural pathways, by blood circulation, and by a skeletal structure that renders the functions that allow you to be you. That is, this is something that none of your organs could do alone. Both of these are simple examples of what we know to be very complex systems. Systems are everywhere, and the identification of them is necessarily a human construct. That is, we get to define the system and its boundaries. We get to identify its pieces and how they connect, and how to distinguish what the system's characteristics are. These are known as its emergent properties. By defining all of these pieces, we allow our minds to work toward a better understanding of the various components of a system and how they interact. In other words, we create a mental model of the system, and this provides us the structure to work toward analyzing what makes the system work as it does and what could make it work better. This is what I will refer to as systems thinking. In many ways, I found that learning basic conceptual ideas of systems thinking was a relief. It provides an intellectual safety valve and a deeper explanation for me of what gets in the way when I am stuck at some level of lack of personal growth, or if I have some inability to express an idea. For me, systems thinking provides not only a means to understand the basic mechanism of how some physical or social systems work, but a means to understand the means of how we understand these mechanisms. Systems thinking promotes a meta view to allow a larger incorporation of how the whole both affects and is affected by the parts. Even without an understanding of the basic tenets of systems thinking and modeling, consideration of the meta view in any situation is usually advantageous and will generally lead to outcomes that are better understood and more aligned with the desires of more stakeholders. Proper systems thinking is indispensable within proper education, in my opinion. As a professor, am I able to dig down deeply to the explanation of a concept and to non-judgmentally appreciate why that concept is or is not resonating for a given individual, or, more so, for a group of individuals who may or may not share common ideologies and who do not share personal histories? More so, am I able to address that gap by adjusting what I describe and how I do it? So how can we approach systems thinking, and how can we use it to better our understandings of whatever we choose to focus it on? The first step is to identify what we consider to be the most important elements of the system. To highlight this, I'm going to ask you a question. When I hold a Slinky, as I am doing now, what are the key elements that make the Slinky respond as it does? If I were in a class, I would take a poll to see what the students think. But here, I'll state some possible elements that I have heard of before. I often hear that gravity is an important element, or perhaps my release of the Slinky. An answer that, however, is definitely in the minority, if it's ever addressed at all, is the fact that the Slinky itself needs to be present. Without the Slinky, there would be no extension and no oscillation, no matter what. This example illustrates that it is sometimes tempting to focus on some elements and potentially ignore others that may be even more important in creating a mental model of the system. Once as many elements of the system as possible are identified, the subsequent step involves considering which elements affect others. This relationship is given the name causality, and I want to distinguish it from the idea of which elements are just simply correlated with one another. Again, I'm going to provide an example. Ice cream sales, believe it or not, are highly correlated with murder rates in major cities. A clear policy implication might be this: we need to limit ice cream sales in order to reduce murder rates. However, despite the clear correlation in the data, I would be hard-pressed to draw a causative relationship between ice cream sales and murder rates. Rather, as the temperature warms, more people will probably buy ice cream, especially from vendors outside. Additionally, as the temperature warms, there'll be more people in the streets, more crowds, more tempers flaring, and more opportunities for conflict. So the common causative thread in this example is the temperature, and we can argue that as the temperature increases, so do murder rates. Also, as the temperature increases, so do ice cream sales. The relationship can be expressed this way. The plus sign refers to a positive correlation between the two elements. That is, as temperature increases, all else being equal, so will murder rates increase. Similarly, as the temperature decreases, murder rates will also decrease. So that plus refers to both of those situations. The same is true about the relationship between temperature and ice cream sales. I can express it all in one diagram like this. Also, note that in the system, the temperature is not affected by ice cream sales or by murder rates. Elements of the systems that are external and that are not affected by other system components are called endogenous. In many systems of interest, most of the elements are affected by other elements, resulting in feedback that in turn affects the causative element. That's not the case here, but let's go back to the Slinky example from earlier. Once I drop one end of the Slinky, it gets longer. As it gets longer, there is a growing force that tends to cause the Slinky to contract. As the Slinky gets shorter, there's another force that in turn causes the Slinky to get longer again, that is, to lengthen. So let's consider the elements of the bouncing Slinky. One way to think about this is to consider a long stretched out Slinky as one element of the system, and a compressed short Slinky as another, even though it's the same Slinky. The act of lengthening can be another element. The act of lengthening the Slinky has a positive causation with the long Slinky. That is, the act of lengthening causes the slinky to reach its longest point, with some delay. Similarly, the act of lengthening the slinky has a negative causation with a short one. That is, the act of lengthening the slinky with some delay causes it to not get shorter, it's getting longer. And these relationships are expressed in these diagrams here. Conversely, the short slinky has a positive causation with the slinky lengthening. That is, when the slinky is at its shortest, it is in the process of getting longer, and a fully lengthened long slinky has a negative causation with lengthening. That is, when the slinky is at its longest, it's no longer lengthening, it's now shortening. I'm going to connect all of these pieces together and tie it all together so that everything we have learned can appear as a loop that defines the system. So what happens and how do we interpret this figure? Well, you can start anywhere you want. Let's say we start where the slinky is at its shortest. The figure shows that when the slinky is at its shortest, it is lengthening. That lengthening, with some delay, brings the slinky to its longest point, which is right here. When at its longest, the slinky is then shortening or not lengthening, thus the negative correlation right here. With some delay, that brings the slinky back to its shortest point and the cycle begins anew. I have 4 points to make about this conceptual analysis. One is that this system, unlike the system with the ice cream and the murder rates, this system involves feedback. This is where one factor affects another, which, in turn, eventually affects the original factor. That is why the slinky will not keep getting longer or shorter forever. It's because of the feedback and the way the feedback works in this case. Another aspect that some of you may have realized is that I could have had another element called shortening instead of, or in addition to, lengthening. I chose to use lengthening rather than shortening very arbitrarily. However, I chose not to use both since they are opposites of one another and can be completely expressed by just using one of them. In other words, when something is not lengthening, I say it has a negative correlation. So rather than using shortening, I say it's negatively correlated with lengthening. If I can reduce the number of elements that I need to consider, I make the system simpler to model and to interpret, and that is almost always preferred. Yet another point I would like to make is that I'm not considering everything in this model. Based on what I described above, the slinky would keep on bouncing forever. If you've ever played with a slinky, you know this not to be the case. The size of each bounce will get smaller and smaller over time until the slinky eventually stops. It's moving much less than it had when I started. In other words, there is a factor that I am not considering. That is the decay of the bounce over time. Could have made the model consider that, but I didn't for this example. Finally, there are no mathematics involved at this point, so the system is completely conceptual in nature. The case of a spring bouncing, including the case with the loss that causes the spring to bounce less, can be very accurately modeled and predicted using mathematics. This approach provides a conceptual way to show that systems thinking can be applied to cases where laws are much less well defined and where the systems are much more complex than in the physics associated with springs. And the physics associated with springs are very well understood. Despite the lack of mathematical rigor in this analysis, it offers an advantage to a purely mathematical approach, as well as a means of remedying the lack of rigor. For one, it allows a much more intuitive and easily grasped means of working to understand and to communicate the dynamics of a given system. Another is that it can be applied in situations other than with springs that are otherwise difficult, if not impossible, to be rigorous with. Consider social systems, political systems, and so on, which have many moving parts, and yet there are relationships whose dynamics can be explored, using this type of approach without having to use mathematics. Additionally, the rigorous mathematical approaches can still be integrated into systems thinking, and they can be done so in a manner that is more approachable to people who are unfamiliar with calculus, which is the building block for some of the system dynamics that can be explored. For the sake of time and for the sake of your attention, I'm going to end this presentation and do another one that will explore more deeply systems thinking using another technique called stock and flow models. These can allow a quantitative approach to systems thinking, more so than the causal loop diagrams that I've illustrated here. I will then apply these stock and flow models to the issue of greenhouse gas-induced global warming.